Welcome to Complexity Made Simple, and my name is Paul Allen. And before we get into today's fantastic video newsletter, what I'd like to talk to you about is all the materials that you can purchase to help to support the channel. We've got these fantastic textbooks that range from the simple statistical process control for small batch production. We've got the 7 quality tools for world-class problem solving, which is essentially yellow belt material. Then we move on to design of experiments for 21st century engineers. Every engineer and scientist needs to be able to do design of experiments. And then finally, drink tea and read the paper. The most fantastic green belt handbook you can buy on the market today, full of practical tips and fantastic physics that'll help you become a world-class engineer and a world-class quality engineer. Of course, you can also click on the link to buy me a coffee and make a donation. That would be fantastic. But at the very least, click on subscribe, click on like the video, because it all helps to support the channel. Many thanks for your help, and now on to today's video. Welcome to Complexity Made Simple. My name is Paul Allen, and the subject of today's video newsletter, well, we're going to talk about the fact that you need to learn and apply Six Sigma in the right order. And this follows on from something, so we're going to say apply Six Sigma in the right order. And as I say, this follows on from something to do with a hobby of mine rather than my job, which is playing the guitar. You can see from the guitars around me, not only do I play them, sometimes I make them. This is one that I made myself. I play them very badly, and just occasionally I look on the internet, I look on YouTube, I get a guitar lesson and I try and learn something. And I'm not too great, but I'm not really doing it properly. And today, one of the lessons, one of the tutors said, if you're going to be good at playing the guitar, and if you want to learn the guitar really quickly, you've got to learn it in the right order. So it's a bit like maths. You learn to add and subtract first. Then, of course, you're going to learn multiplication and division. Then you're going to learn long multiplication, long division, fractions, decimals, that type of thing. And you will learn it all in the right order. And as I watched that, I thought, well, that's exactly the same as Six Sigma. You've got to learn it in the right order, and then you've got to apply it in the right order. So let's talk about learning Six Sigma and applying Six Sigma in the right order. And of course, you know, the DMAIC process is about trying to make you apply it in the right order. So that's there to try to help you in the right way. But one of the key things about Six Sigma, everybody thinks it's about mathematics. It's about collecting data and it's about mathematics. And it isn't. What Six Sigma is about, it's about physics. And that's why it works. It's about applying the laws, simple laws of physics. And then the mathematics help you to do that. And if you think of it in that order, the maths will have some value, the maths will have some sense, and you will achieve something. Because Six Sigma to me is about fixing technical problems. It is about world-class technical problem solving. So it's physics first, it's maths second. That's the first thing on a generality. But what sort of physics? Let's have a look. What's the first thing you got to get in your head? It's very simple. Number one, every process looks the same. You have a process, you're trying to use it to make money. It's got inputs, and of course it's got outputs. On the output side, Because this is normally where you see your problems. You're letting your customer down in some way. You're missing a tolerance, or you're missing delivery dates, you're missing quantities, etc. And that's where your problems lie. But here's the basic laws of physics. If you want to make these go away, your solutions have to be over here. You have to go to the input side. So inputs, control, outputs. It's really simple, and everything starts with that. That is principle number one. Then we can build on this. Okay, your problems. Well, basically, there's two things that could be happening to your process. If I look at problem type 1 looks like this. You have your process being very repetitive, very well controlled. It's doing something you want it to do all the while. Let's say there's a target here. You want to be above this target. No problem at all, okay? So that's where you're trying to be. You're constantly above that target. Everything's great with your process. And then you get a problem, or you get a problem like this. In other words, the average shifts. So if I drew this as a distribution, the distribution was sitting in the right place here. It was all good. And now maybe the distribution has shifted. Now that is a shift in the average. It is a shift in the signal. Okay, so laws of physics. Here's your process. How can your process behave? Laws of physics, how do processes behave? There's either shifts in the average, or the shifts or problems with the spread. So in other words, the spread problem would look like this. Maybe the same target. But instead of this lovely stable process, what you've got is this wild, chaotic, swinging around. Sometimes we're above the target, but lots of times it just process goes crazy, and it's just all down here, got lots of problems here. Now this is not about signal. You don't have control. The process isn't sitting in one place. This is about noise. This is all about noise compared to this being all about signal. So if I drew the same diagram, what do we have? Well, we have our specification on our diagram, and basically what we have is a process that just simply isn't capable. It's just generally, its ability to stay above the target just isn't there. Now that's a problem with noise, that's a problem with signal. Now typically, sorting out a problem with signal will take a matter of hours. This type of problem is not a Six Sigma problem. By the way, this is the type of problem that Toyota have most of the time. It's the reason why Toyota say, we're not going to do Six Sigma, we're not interested, we do lean. Because Toyota are in control most of the time. They've got good consistent processes that are well controlled, and therefore they're not going to use Six Sigma because solutions to them take a matter of hours. Down here, however, you have no control. And gaining control is the problem, removing the noise. So are you trying to move the signal, or are you trying to remove the noise? Now this is the physics you've got to learn. Here's the process. Here's the problems. That's the first thing you should be looking at. It's the first thing you should look. There's no maths in any of this, by the way. There's no mathematics here. This is just physics. Okay, so now, no control. How long will it take you to fix an uncontrolled process? Well, it's not going to take you 3 hours. What it's going to take is 3 months. This will need a team for you to do this. This up here, one person can do this. usually in a matter of minutes or hours. A team is needed here because this is about policies and procedures. Your maintenance policies and procedures, your training policies and procedures, your raw material purchasing policies and procedures, the targets that you set, all kinds of things. This is hard yards, but this is a Six Sigma project, and it's going to take you 3 months. It's going to take you 3 months to fix it. So apply Six Sigma in the right order. Apply Six Sigma in the right order. What should you be doing? You should be asking the question, what type of problem do I have? Do I have a problem with signal, or do I have a problem with noise? Is it going to take me 3 hours to fix, or is it going to take me 3 months to fix? No maths in this at all. Now, if you think about define, measure, analyze, improve and control, where are we? We're simply in this phase. We're in the define and the measure phase. I don't split them because I think you have to measure in order to define the scale of your problem. So we're in the define and the measure phase. But the first thing I want to define is not how much money I'm losing. It's not the problem itself as such. I'm not trying to quantify the problem. I'm trying to just understand the problem. Is it signal or is it noise? And that's the first part of the define process. Because if you don't have a problem with noise, you don't have a Six Sigma project. You have a simple problem solving project. It's not even a project. It should take you a few hours at most to fix it. So it's the first thing. Now, obviously when you start to go, what am I going to do with this? So you go, there's the physics, there's the problem. It's a problem with noise. It's going to take me 3 months. I'm going to pick a team. Here's the order that you can see, the order that I'm applying this in. The first thing I'm going to ask, am I in chaos or am I in control? This is chaos, this is control, because only chaotic processes really are Six Sigma projects. If you don't do this, you pick projects that you don't need to work on. You pick the wrong projects. You don't understand what tools to use. What am I going to do here? Well, I'm going to identify every one of these. So I'm going to identify every variable, every input, x1, x2, x3, x4, x25, x55, x65. I could end up with 100 variables here. And then I want to know, how do we control them? Because this is a function of many inputs not being properly controlled. Now look, there's no maths at this point. I'm still talking physics. I know what causes this. Lots of variability on the input side causes lots of variability on the output side. I'm doing it in a particular order. There's the physics, there's the problem. Right, identify the physics, identify the inputs. Am I fixing them or not? Do I have rules? Do I actually control them? Where don't we control them? If we don't control them, we'll put rules in place. The more you reduce the variability coming in, guess what you'll do? The physics kicks in, the more you reduce the variability coming out, and you can start to produce a process that starts to look more like this. That's the order that you do Six Sigma in. Now, once you've done this, then you start thinking about the maths. Can I do it cheaper, better, faster? Can I get design of experiments out the box? Do I need hypothesis testing? Do I need an SPC? Because of course you're going to try and control this. Do I need statistical process control to keep it under control? All the maths starts to come out of the box once we've got rid of the noise. But the maths is the last thing. Physics leads Six Sigma. Physics is at the heart of Six Sigma. And if you don't do Six Sigma in the right order, if you start with the maths, too many courses, too many Six Sigma courses, where do they start? They start with teaching about statistics. They start with teaching about maths. If you don't understand physics, maths is no use to you whatsoever. So apply Six Sigma in the right order. Physics comes first, then we'll start thinking about the mathematical tools to help us to understand the physics. But actually, when you understand the physics, this is really easy. I don't need much maths to fix this. Six Sigma to me, I can fix any technical problem. I just draw this diagram for your process and I ask you a question. How do you control this? 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 And if you tell me you don't, I'll make you control them. And that's it. It's as easy as that. Six Sigma is really, really easy if you apply it in the right order. And if you apply it correctly, guess what you'll do? You'll make pots and pots of money. Your processes will never ever have worked so well. Do Six Sigma in the right order and make pots of money.